Hello, what's going on? It's Jun-chan, and we're back on stream doing some Comonadic Explorations. So let's just jump straight into it. Yeah, I need to set up an alarm because today I'm going to be doing an hour and probably not much more. All right, let's go for it. So let's do a little bit of our housekeeping and duplicate our log, and we are doing Comonads. All right. So what did we write earlier? Yes, we had a Stack Overflow. So where were we? We were, let's take a quick look at our code. We were in a playground, so using Node.js to try and do some basically design of how we want our Comonads to work for us. And so we did this, what is this noise? Oh yeah, okay, maybe I'll, that was the pure script Discord, which, yeah, which I suppose at some point maybe I should have available somewhere here, because they probably, people can help over there. But I'm a little bit shy, and I suppose I also learn maybe better by trying to find things out by myself, at least up to a certain point, right? But I think we are making some progress. So what do we have here? We have a bunch of stuff we're not exactly using right now. Previous experiments trying to understand the co-free explore and how it could be or not be useful for us. Then we move some of the type machinery that we use in our in the Comonadic UIs, but without the UI bit, in fact, we instead of being in React components, the React monad, the React element monad, I think it's called, we're in effect strings. So our UI are just strings, and our interpreter right now are using we're trying to basically have monadic actions in the base functor, the core of the base functor, which is similar to what Phil Freeman was doing for this particular bit of code. And then trying a counter interpreter, which I suppose at this point we've tailored to try and fit the code of explore here. No, that's not right. Of a few things, but yeah, explore is one of them. But the other is, I think, was it builder? Not builder, but maybe the code in builder. So it's not difficult free. What we started doing, and maybe that was premature, I'm not so sure, but we try, we try to fold state inside our interpreter, because with this, with the PureScript React basic approach, we end up having eval, which take this the current state and returns the current state, and then render takes the current state, and in fact it sounds like really what this means is that we're composing things with a co-state comonad, so a store comonad. And so I've been having this intuition for a while, and I'm trying to make it so. And what it looks like then is that our counter interpreter needs to be in counter, which now includes store T, so comonad transformer, with the state counter model and the base comonad co-free counter interface. So that makes things slightly more complicated, because now our inc probably needs to be lifted inside or lowered maybe in our Comonad stack. And then I think now our counter interpreter needs to be in the larger monad, and and counter interpreter, right, is something we pass to, right now we pass to differ co-free in order to build a co-free of what are we trying to build? We're trying to build a co-free of right. So we're using the store_t constructor here. I think we could use probably the store_t. There must be a store_t constructor function. No, let's see. Okay. Co-free trans. That's lazy. Okay, so let's go to store_t. And no, we have a run store_t, but building a store_t really is done by using the constructor. So we pass a builder, and a builder is something that that has the base comonad in front of it, which is why we have co-free counter interface as the W here. And then we need to pass it a function from S to A in order to get a store_t that is in S. So that's our S, and our A is the return type that we want for what? The return type, well, the carrier type, right? So the carrier type apparently is this beast. Is that meant to be that? Let's double check again. I mean, a component is that beast, and so I think, right? Oh no, a component is actually a W of this, where W is what for us? Our W is counter actually. So we are. So why are we're trying to build a component counter overall, and so right. So the intuition is a component counter has a store_t on the outermost layer. That's why we create a store_t in there, and then in order to get a store_t, okay, maybe we need to. Yeah, that's no. What we want is a store_t of counter model and W is a co-free counter interface, and A is what we have in Explorer in here is UI code W unit. Am I right? I'm a little bit unsure right now. Let's go back down. Okay, so component counter, we're saying, okay, I didn't put that in my clipboard. Okay, component counter is of this type. So a component of a W is indeed a counter. A component counter is, okay, well, a counter of UI of co-counter unit. And that, given that counter is store T counter model, blah, blah, blah. And then what we have is this pretty impressive mess. And we can, let's not unroll this W here. Okay. So when we do component counter here, let's no, I'm not going to remove the indirection because we might need to reuse this machinery to do an initial round of initialization. So let's not do that for our handlers and whatnot. Okay, so store T of counter model of co-free counter interface. What we want is then the inside to be something like this, right? And so when we do store T tuple of a builder which has this crazy type, then we indeed returning into UI co-counter unit. So that's our A, right? So yeah, so it will make sense. We do S to A, and then that's the, and it is wrapped in a W. Is that the right? Yeah, I think that's the right W. Yeah. And then we pass it an initial S, right? And in our case, our initial S is just count 0. So our builder should be able to basically deal with, it's basically doing a little bit of that CPS thing as well. It's creating a comonad full of something waiting for counter, and then I suppose the store T comonad is going to manage to thread state for us. Yeah, as long as what we return is a comonad that is, I suppose, in the next that is ready to that does whatever it does with the current counter, whatever it needs to do with the current counter, right? Our counter model. So, but that I think I managed to figure out, in fact, right? Because what we're doing in the end is that we're creating a co-free by using differ co-free. That leads us to this question of how do we avoid the stack overflow. We were trying to basically deal with laziness here properly. And differ co-free should allow us to deal with laziness properly. And so here we are trying to build a co-free FA by passing a tuple of A, and render has type counter model to UI co-counter unit. So it has the type we want. And then passing an F co-free FA. And what I was surmising is that I could do that by passing the same render function to counter interpreter, having modify counter interpreter to take, say, the renderer and then do some crazy things in it. So let's try and make sense of this just a tiny bit more. I think what I should really do probably before diving into this is drill down a bit into Comonad transformer stacks, because I haven't written any and I'm trying to just launch off into pretending that I know how to use them without having even done a simple example of them and done a simple example of that S2A and understand how state threading works and whatnot. So I think that's what we're going to do, right? Because we have code that actually compiles. So let me add this into the log right now as a ongoing thing. Learn or try out simple Comonad transformer stack. So let's do that, and we'll do that. I'm in the wrong thing here. So we'll do this before this. Okay. Comonadic UIs in effect string instead of r.react element. Okay, trying out Comonad transformer stacks. Okay, so shall we just try with store T without with the identity Comonad? Yeah, I suppose that makes sense. So let's just do type stack is store T of state's going to be let's just counter model. No reason not to. Identity and A. We do have kind of a crazy A in our case. So maybe we pick the simplest one for now. And then we'll say that we'll create a stack by doing store T of our builder thingy, which now is going to be a tuple of the identity wrapper of a function from well, a function f, and a state count 0. And our function f is going to be of type counter model to identity, to unit actually, which is very uninteresting to be honest. So maybe we should make it to int. Okay, and then we'll say, well, something like just return the count. And running equal here. Okay, stack I think is a duplicate. Yeah, so Comonad stack. Identity, do we import? And then tuple. Yes, wrong place. And stack defined multiple time. So let's call this Comonad stack. And apparently we compute here. So we have a Comonad now, and the way that we would be using it in the component case is by passing it some explorer, right? But I suppose what we want to do here is just run the store T Comonad, right? So let's just do that. And I think I'm looking at store here, and I'm wondering whether I just haven't completely confused myself with what the store Comonad is, and just assume that it was actually pretty much state. So let's see whether that's true or not. Okay, what does this mean? It means that here, We'll probably need to comment that out. And do something like logging, well, run store t. Okay. Pass and peak is what we have. So we want to peak. Yeah. Store is definitely not threading state. Let's finish this thought. We don't need to run it. We can just say pass of Comonad stack. How about that? That should give us count 0, I suppose. And okay, yeah, it's of type count int, and so we'll want to do a dot count. How's this work already? It might work. We might need to show, but yeah, it does work. So let's Spago run, and we get 0, which is what we expect. And so now if we peak, let's if we peak and at some particular s, which would be, for instance, count 1, peak is not imported from control Comonad store. I think we need it from class, right? It can just be 1. That's what's happening here. Yeah. Maybe? No. Hold on. Peak. Peak gives us the Comonad again, doesn't it? Peak takes an S and a Comonad and returns an A. Right, so we don't need to count. Is that right? So we should have 0, 1. Yeah. Okay. That's just precedence again. Just like this, but okay. That's a little bit ugly. To be honest, we can do that. Okay. So now I'm thinking about recursion schemes, because it seemed to me that if a fold can be built from a comonad, which seems to be the case from some of the papers that, or some of the blog posts that we were reading, then that's what we need to do. And maybe it's not about using the store comonad as is, but rather, but I think I should figure that out, because then the question becomes, can we just compose our component together with that in order to get a recursion scheme that will thread state? Let's see. Recursion schemes from comonads. There's a paper. And there's Ed's library. And the full text. Okay. So fold, fold. Yeah, it's not easy, huh? Okay, so first of all, what is the recursion scheme you want? I think it's isn't it an anamorphism? Yeah, the base functor formulation. There is a post about that. That's cool, because I wasn't sure about this. Okay, but oh, actually, PureScript recursion schemes. I haven't looked at whether there was a. There's not a library for it, but there's a couple of blog posts. Okay, that's cool. And here, those are just links to the thing. And no, there is this Matryoshka. Yes. Well, let's look at the docs. I remember using this before. And so we kind of want folds, and so kata is a fold, and the equivalent of base, I think, here is recursive. Let's check the similarities here. Not this. I think we'll won't use that. And kata. Right. So kata takes the way that this is laid out is different. And we have a recursive TF. Or base TA, taking a T and returning an A. So really, I think it's both the algebra FA and the recursive TF together that replace base. Okay, so we should probably pay more attention to what's happening here, because it seems like it has all the things we want. But we'll probably need to walk through it, though, trying to squint, see whether we can understand how this works. But I think what we want is a catamorphism. And I think this tells us what we do at each iteration, hopefully. And this, let's look at whether there's a test. There are some tests. There's an example. That's good. And oh yeah, I wanted to have this here. Yep. And expert and lists. It's not. There's a base functor here. There's a use of algebra. Okay. Prod. The prod algebra being catad here. Okay, so that's good. Let's import Matryoshka here. Let's install it. Let's import some stuff. Like this. And let's do the same prod. So we're moving into the land of recursion schemes from Comonads. And we are going to do this. Matryoshka was not found. Just need to spago build maybe. And we want this stuff and cons. Cons, and we'll need nil. And then this stuff is actually also defined here. Okay. Sounds good to me. Boom. How's that? Tacit string. I have no idea what that is, but apparently it's a thing. Never heard of it. Interesting. Could we just make this a string? I don't. Okay, let's avoid the paper. Fixed points. String to tacit string. Okay. No examples. And just this. And how's it defined? It's just a new type around string. But there's no documentation at all. But it's linked to the functors for some reason. Let's see whether it's used anywhere we can see. Not here. Okay. Well, let's import it. That means we're going to need to import. Do we also need mu here? List is mu list fa, so yes. Okay, so we'll need to import the fixed points as well. And with the I here and fixed points. And untype list because I indeed didn't get that guy, which is the fixed point of this def functor. And for some reason, that's just for the show that the tacit string is used. No idea. No idea at this point. Let's just copy things and then poke it. Okay. So in theory, we should have something like, I don't know, 25, 24, yeah, which is simply 1 times 2 times 3 times 4. 3 times 4 is 12, 2 times 12 is 24. And so we use the prod algebra. Let's look at the code here. Prod algebra, which knows what to do for the base case and knows what to do for the following cases. And for the following cases, it's getting the current value in H, and then it returns the folded value. So that's the recursive case or inductive case, one of the two. And so that's kind of what we want to do. But I suppose here, I guess I don't see the comonads. And so let's see how and why. And maybe there's a comonad instance for algebra, maybe not. About algebra. So there is a relationship between algebra and the comonad that I don't know from the top of my head, but there is class recursive, and that's a way to that's a way to fold things. Does this have a lazy in there? That's the class. Yeah, but no, it doesn't. Pattern co-empty. That's a pattern functor for free. It's not reader. Job of empty. That's a comonad. It's not made obvious here, but it's used when we recurse. Is that right? What's its how is it built? Does this have a lazy in it? It does not. Just a basic functor. I mean, at least that's what's used here. And so, but when we use it for recursive, it's just to say that. So I suppose that means that out of a fixed point in nu, we get a fixed point nu f, we can get an f. Is that that what this means? project is unroll. These feel a bit like pairs. T defines the F. Mu has an unroll. I suppose I should take a look at mu. No fixed point here. So let's go check out fixed point. It's the list fixed point of a functor f when it exists. And it has the tacit string for show only, which is compositional, whatever that means. So we only need to be able to show a single layer of structure. Okay. And unroll takes a mu f and returns an f of the mu f. And mu has the in and just recurses. And so project just take a mu f and return the f, which is an f of mu f, I suppose, in this case. Unroll takes the f and returns an f, which is an f of mu f, which is just one peeling, right? Removing one layer of the fixed point. And so this allows us to do exactly the same for different versions of the fixed point, including so coenv. Let's look at coenv again here. Coenv t is a monad transformer. Or is it a comonad transformer? Like the fact that this uses a W and that doesn't have also monad instances or comonad instances is a bit hard. There's some example there. Stack usage. Oh, hey, look at this. JavaScript based things. Already for the trampoline, stack safe function composition. This all looks quite interesting, but not what we want. And indeed, there's not enough documentation. And where is meta? There's such a thing as a metamorphism. Coalgebra and algebra. Is that pairing again in a different shape? Okay. There's some original Matryoshka docs, except there isn't. So it's not reader, it's the dual of empty. And you're saying empty, this is run empty. So it's not even run co-empty. Should be run co-empty. Strange. And okay, it's here, but how is it used already? In class recursive and co-recursive. Saying mu is the listf of A, and listf takes an A and a tail, and the tail, so that makes total sense. Here I'd be used to use free, but here we're not using free. But I suppose this kind of means the same thing here, is that we could maybe use free, and in that case we should still be able to recur through it. Let's see if that's true. Yeah. Okay, so okay. Let's see whether this really is this. No. Free should take we're going to need to use a compose or something. If I was writing this as a pattern functor for free functor, wouldn't I write it like this? But that would be wrong, right? Because indeed we need a t there. Okay, now I'm trying to see. Right, tuple RA. So indeed, we're just carrying an A that is sort of dangling in the free construction. So it's a bit like, well, to be honest, it's the B, and we're carrying a B. And then if we're trying to use that, we can't really use this. We need to create cons and nils specifically for it. Let's try. And this would be for, yeah, same liftaf though. So no, it would be the same liftaf. Okay, so can I construct a list prime? Right. Right. So can I do this prime int? Yeah, indeed, I don't know how to pass it something else, but let's just try something related. Right, so I can't make it all of a sudden have a different type. Okay, well, let's have some list prime and see whether we can make that have a different type. Okay, we are maybe getting somewhere. So instead of actually being able to return an f from our mu, so some list is list of int, which is mu list of blah, and now we have list prime in string, which is free of list fa b, and so we'd want to we'd probably want a const prime and prime. And what would they do? So I suppose we need to look at the code of kata, which probably uses project. And maybe there's a more generic kata that we can use here. So probably the type of algebra. No. Algebra is FA2A. So prod is FA2A, and that's not a problem. Is it about prod? FA2A. Is that just using, I don't see the constraints that are useful for me here. Is this in kata then? Yeah, kata takes a recursive TF. And so we need an algebra. Right. Okay. I think I'm getting there. So this implies that kata will have this type. And what we really mean here is That's a bot. Go away, bot. Sorry about that. Come on, bot. My yeah, my browser is super slow because I think I have way too many windows open, and I'm not using Chrome, and I don't know why I'm not using Chrome. I should be using Chrome. Okay. So what were we saying? We're saying that this really implies that our f is listf a, so we're using the recursive instance of basically int listf int, and that's all good, except that if we want to do the same thing here, and that's really, yeah, that's fine. Then in fact what we're aiming to go towards with our prime here, and an int string in addition to that, is we need the recursive instance of coenv a, so coenv string, and f, which is listf of int, I believe. Listf prime of int. Is that right? F free mu free, that's our f. Oh, right, so I'm wrong. This is the listf of int, and our f is this, and coenv string should be of env of listf int here. That makes sense, and then string here, yeah, and that will be paired with free, not this, but free listf int string. Yes. So what this means is that we need a prot prime of type algebra listf int I think we need it to be actually the whole thing. Free listf int string to coenv t string lift listf int. Let's list here, and then, well, then we need to find some implementation that works, but before we do, let's try and see whether that will actually fix the types if we do this now. Well, we need to import coenv t, which isn't much. Where is it? It is in Matryoshka. Let's keep this here. conf t right there. And I'm going to have to let things go here. We'll have a conf t, but free f. Okay, so maybe free f like so. Would that work? And no. It feels like we actually need the carrier types here. But you want algebra to be, yeah, I mean, it's true that it's not an algebra really. So let's see which document the rabbit hole we went into right here. So we tried out a simple Comonad example stack, but we found out that store is not state. Duh. So we're basically going to try to thread states with recursion schemes from Comonads. And then we kind of stuck into trying to, well, we've ran the Matryoshka examples, so we can at least cross this and this. And we're trying to see how to use free instead of mu, and we don't even know really what it even means, but we want to play more with kata as a state threading solution, and then which Comonad is that. So we probably need to read more about the Comonads as part of recursion schemes, trying to maybe redo some of the examples here and understand how, having used the recursive and base and algebra, all of that, the differences between we probably need to say this sort of adapt this to a Matryoshka. All right, so that's it for me, and yeah, that was a little bit short and also maybe not a lot of sense that we move forward, because we're kind of exploring the space here, trying to find out whether there's a way to thread state that is kind of comonadic, and see whether we can use that to feed into our how we build our interpreter and how we advance our interpreter. To me, that makes sense to do that, because I like to understand those building blocks that are very abstract, but to really understand how to build things then in Kit. And it seems like that this idea of regression and fixed points and understanding free and co-free in terms of that, and then understanding how to roll and unroll those values, and then maybe use them to also thread state. That seems like that's exactly the type of stuff that we were trying to do with Explorer and with our builder here. And so if we can find a more something that is built from those building blocks, then I feel like that will give me a better understanding of the building blocks and make at least things for me a little bit more clearer when we try to build more complex things with them. So that's it. Thanks a lot for watching. I'll see you on Saturday afternoon for more of this. Bye bye.